Yeah. Hello, everybody. So this is group 8, and we're presenting on binary classification of pneumonia versus normal chest X-rays using deep learning. So pneumonia, it refers to an infection in the lungs caused by inflammation of the alveoli. This cells can be filled with fluid or pus, and the symptoms are chest pain, cough, shortness of breath, fever. So the problem statement is this just tries to come up with early diagnosis, which is important for timely treatment and improved outcomes. So they're usually doing the manual diagnosis, which is time consuming, human errors, and specialist dependency. So this is just the project background, our main objectives and goals, which is to come up with artificial intelligence, especially deep learning, showing automating chest X-ray interpretation. Literature and prior work, what people have done so far and how far they have gone so far. Project objectives, the main objectives is to develop a deep learning model to classify chest X-ray images into normal and pneumonia. So the expected outcome is to be able to assist healthcare providers, improve efficiency and reliability. Data and pipeline architecture. So we use the dataset from Cargo, NIH's X-rays, and the pipeline is load and organize data, exploratory analysis, pre-process of and resize of data, build and train models, evaluate results, compare architectures, and grad cream explainability. Models used, we use the custom CNN architecture, ResNet 50, DenseNet 121, and EfficientNet B0. So we use the binary classification, and we use sigmoid, and also we use binary cross entropy. So these are just a screenshot showing the results and model efficiency for the CNN. This is for the DenseNet. This is for the EfficientNet. This is a table showing performance metrics summary. So thus is model architecture.
So for our model architecture, since we chose ResNet 50 as our base model, so this is its architecture. It takes in an image of size 224 by 224 by 3. Then before we move on to the extraction layer, we do some data augmentation and preprocessing. For example, horizontal flip, small rotation, zoom, and contrast adjustment. And then in the extraction session, we have our upper layers and our lower layers. Our upper layers are unfrozen and trainable, whereas our lower layers are frozen. Then after that, we did global average polling instead of max polling. And then we move on to the classification head, which is a dropout of 0.4. Move on to the dense layer with 128 units and an activation function ReLU. Then we do another dropout of 0.3. Then we have our flat layer with 1 neuron and an activation layer or sigmoid. Then this is the output for the block. It classifies our image as either normal or having pneumonia. Then I'll move on to the code demo. Okay, so this is our code. We started off by building the model in another Jupyter notebook. So this Jupyter notebook is where we are going to import our model from where we saved it. We had saved it in the what's it called in Google Drive. So we import our libraries, load the model, connect our Jupyter notebook to connect Google App to our drive where the model is stored. Then this is the architecture of the model. Uh, then so for our model, we are going to feed it some images. For example, image with the index number 18. If we run this cell, it's going to give us a prediction of normal being 99%, uh, which is true when we compare to our true label. So for another example, if I run it on index 400, it gives a classification, it gives a prediction of pneumonia. Then for our true label, it's actually pneumonia. So this is how our code runs. Then as for the grade cam, so this is an example for an image that we loaded to our grade cam model. It's showing that the upper borders are the ones influencing our model, which doesn't make a lot of sense because we're expecting our model to be making predictions around these regions over here. So our model is actually coded predicting numerical values, but it doesn't classify well when it comes to when it comes to Gradcam. So So for conclusions and future work, we successfully built a successfully trained a ResNet 50 model to train our images, and for future works, we are expecting to add more data and build a multi-class classification model that's able to distinguish between different lung diseases. Thank you very much. Wait, stop again. Yeah.